Can 100% renewable energy power the world? Every year, the world uses 35 billion barrels of oil. This massive scale of fossil fuel dependence pollutes the earth and it won't last forever. Scientists estimate that we consume about 4% of the world's oil. According to present estimate, this rate will run out of oil and gas in 15 years or so in about a century for coal. On the flip side, we have abundant sun, water, and wind. These are renewable energy sources, meaning that we aren't used it over time. What if this changed our fossil fuel dependence for an existence based on solely renewable? We've pondered this question for decades, and yet renewable energy still only provides about 13% of our needs. That's because reaching 100% requires a renewable energy that's inexpensive and accessible. This represents a huge challenge even if we ignore politics involved and focus on a scientist and engineer. We can better understand the problem by understanding how we use energy. Global energy use is diverse and complex system, and the different elements require their own solutions. But for now, we focus on two of the most familiar in everyday life: electricity and liquid fuels. Electricity-powered blast furnace, elevator, computer, and all manner of things in home, businesses, and manufacturing. Meanwhile, liquid fuel play a crucial role in almost all forms of transportation. Let's consider the electric version first. The great news is our technology is already advanced enough to capture all that energy from renewable, and there is ample supply. The sun continuously radiates about 173 quintillion watts of solar energy at the Earth, which is almost 10,000 times our present needs. It's been estimated that surface that spans several hundred thousand kilometers would be need to power humanity at our present usage level. So why don't we believe that? Because the other factors in the way, like efficiency and energy transportation. To maximize efficiency, solar plants must be located in the area with a lot of sunshine year-round, like desert. But those are far away from dense population regions where energy demand is high. There are other forms of renewable energy we could draw from, such as hydroelectric, geothermal, but they also have limits based on the availability and location. In principle, a connected electrical energy network with power line crisscross across the globe will enable us to transport power from where it's generated to where it is needed. By building a system on this scale faces an astronomical price tag, we can use newer advanced technology to capture energy more efficiently. The infrastructure for transporting energy would also have to change dramatically. Present-day power lines lose about 68% of energy they carry because the wire material dissipates energy through resistance. Longer power line would mean more energy loss. Superconductors could be a solution. Such material can transport electricity without dissipation. Unfortunately, they only work if cooler to low temperatures, which require energy and defense and purpose. To benefit from the technology, we need to discover new superconducting materials that operate at room temperature. And what about the all-important field-derived liquid fuel? The scientific challenge there is to store renewable energy in an easily transportable form. Recently, we've gotten better at producing limited batteries, which are lightweight and have a high energy density. But even the best of these store about 2.5 megajoule per kilogram. That's about 20 times less than the energy in 1 kilogram of gasoline. To be truly competitive, car batteries would have to store much more energy without adding cost. The challenges only increase for bigger vessels like ship and plane. To power across Atlantic flights for a jet, we need a battery weight about 1,000 tons. These two demands a technological leap toward many higher energy density and better storage. One promised solution would be to find an efficient way to convert solar into chemical energy. This is already happening in the lab, but the efficiency is still too low to allow to reach the market. To find novel solutions, we will need to create activity, innovation, and powerful incentives. The transition toward all new renewable energy is a complex problem involving technology, economics, and politics. Priority on how to tackle this challenge depends on specific assumptions we have to make when trying to solve such a multifaceted problem. But there is ample reason to optimistic that we get there. Top scientific minds around the world are working on this problem and making the breakthrough all the time. And many governments and businesses are investing in technologies that harness the energy all around the earth. TED is non-profit. If you value our work, please consider supporting the page.com/TED. Every year, the world uses 35 billion barrels of oil. This massive scale of fossil fuel dependence pollutes the earth, and it won't last forever. Scientists estimate that we consume about 40% of the world's oil. According to present estimate, at this rate we will run out of oil and gas in 50 years or so, and it's about a century for coal. On the flip side, we have abundant sun, water, and wind. These are renewable energy sources, meaning that we won't use them over time. What if we exchange our fossil fuel dependence for an exchange based solely on renewables? We've pondered that question for decades, and yet renewable energy still only provides about 13% of our needs. That's because reaching 100% requires renewable energy that is inexpensive and accessible. This represents a huge challenge. Even if we ignore politics involved and focus on the science and engineer, we can better understand the problem by understanding how we use energy. Global energy use is a diverse and complex system, and different elements require their own solutions. But for now, we are focused on two of the familiar in everyday life: electricity and liquid fuels. Electricity powers planes, forests, elevators, computers, and all metal things in homes, businesses, and manufacturing. Meanwhile, liquid fuel play a crucial role in almost all forms of transportation. Let's consider the electric portion first. The great news is our technology is already advanced enough to capture all the energy from renewable, and there's ample supply. The sun continuously radiates about 170 quadrillion watts of solar energy at the Earth, which almost 10,000 times our present needs. It's been estimated the surface that spans several hundred thousand kilometers would be needed to power humanity at our present usage level. So why don't we believe that? Because there are other blockers in the way, like efficiency, energy, transportation. To maximize efficiency, solar plants must be located in areas with a lot of sunshine year-round, like desert. But those are far away from densely populated regions where energy demand is high. There are other forms of renewable energy we could draw from, such as hydroelectric, geothermal, and biomethods, but they also have limits based on the availability and location. In principle, a connected electrical energy network with power line across the globe would enable us to transport power from where it's generated to where it's needed. But building a system on this scale faces an astronomical price tag. We can lower the cost by developing advanced technologies to capture energy more efficiently. The infrastructure for transporting energy would have to change dramatically. Present-day power lines lose about 6 to 8% of the energy they carry because wire material dissipates energy through resistance. Longer power lines would mean more energy loss. Superconductor could be the one solution. Such materials can transport electricity without dissipation. Unfortunately, they only work if they cool to low temperatures, which requires energy and defeats the purpose. To benefit from technology, we need to discover the new materials that are operating at room temperature. And what about the all-important fuel-derived liquid fuels? The scientific challenge there is to store renewable energy in the easily transportable form. Recently, we've gotten better at producing lithium-ion batteries, which are lightweight and have high energy density. But even the best of these store about 2.5 megajoules per kilogram. That's about 20 times less than energy in 1 kilogram of gasoline. To be truly competitive, car batteries would have to store much of energy without adding cost. The challenges only increase for bigger vessels like ships and planes. To power across the Atlantic Light project, we need a battery weight about 1,000 tons. This too demands a technological need toward material higher energy density and better storage. One promising solution would be to find efficient ways to convert solar into chemical energy. This is already happening in the lab, but efficiency is still too low to allow to reach the market. To find novel solutions, we'll need to creative innovation and powerful intensive. The transition toward all renewable energy is a complex problem involving technology, economics, and politics. Priority how to tackle this challenge depend on the specific assumption we have to make when trying to solve such multifaceted problems. But there's ample reason to optimize we'll get there. The top scientific minds around the world are working on this problem and making breakthroughs all the time. And many governments and businesses are investing in technologies that harness the energy all around us.